Good morning, everyone. This is Sajin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. In the previous lecture, we discussed about the stability of a control system. Now we are going to start the root locus system. So what is exactly the root locus means? The characteristics of a transient response of closed loop control system are related to the location of the closed loop poles. If the system has a variable loop gain, then the location of the closed loop poles depends on the value of the loop gain chosen. It is important that the designer know how the closed loop poles move in S-plane as a loop gain is varied. Even the introduce a graphical method for finding the root of the characteristic equation known as the root locus method. The root locus is used to study the location of the poles of a closed loop transfer function of a given linear system as a function of a parameter, usually a loop gain given its open loop transfer function. The root corresponding to a particular value of a system parameter can then located on the roots locus of the value of a particular parameter for a desirable root location and can be determined from the locus. It is a powerful technique as an appropriate root locus sketch can be made quickly and the designer can visualize the effect of varying the system parameter on root location or vice versa. It is applicable for single loop as well as multiple loop system. Now we are moving towards the root locus concept. To understand the concept of underlying the root locus technique, consider the second order system as shown in the following figure. See here, the R of S is given as the reference input, where the C of S is given as the Laplace transform of the output. Here, E of S is denoted as the error signal and K upon S into S plus A is noted as the gain of the system, where K and A are the constant. The open loop transfer function has two poles, one at origin and having S is equals to 0 and the order at S is equals to minus A. The closed loop transfer function of the system is shown in figure. Here, as per the definition of transfer function, C of S upon R of S is equals to G of S upon 1 plus G of S into H of S. And as per this definition, here we can write K upon S square plus AS plus K. The characteristic equation of a closed loop system is obtained by setting the denominator of a right hand side of the equation 2, which is equals to 0, and that is 1 plus G of S H of S is equals to S square plus AS plus K is equals to 0. The second order system under the condition is always stable for positive value of A and K, but its dynamic behavior is controlled by the root of this equation 3 and hence in turn by the magnitude of A and K, since the roots are given by S1 S2 is equals to minus A upon 2 plus minus under root of A square minus 4K upon 2A is equals to minus A by 2 plus minus A by 2 whole square minus K. Above equation can show that the system parameter for A or K varies, the root changes. Consider A to be constant and gain K to be variable, as K is varied from 0 to infinity. The two roots S1 and S2 are described loci in the S plane, and root locus for the various ranges of k are given as k is equals to 0. The two roots are the real and coincide with the open loop poles of the system. S1 is equals to 0 and S2 is equals to minus a. Also, value of k is lies in between 0 to a square by 4, and this is the root and real and distinct. Also, k is equal to a square by 4, that is the roots are real and equal, and value of k lies in between a square by 4 to infinity. The roots are complex conjugates. It has been drawn by the direct solution of the characteristic equation, and this procedure becomes tedious and even graphically produced help in sketching the root locus quickly. The characteristic equation of the system is given by delta S is equals to 0, where delta S is the determinant of the signal flow graph of the system. Thank you.